Okay, so this is module 5 of Optimize and Scale. And I actually was able to get my little pies working in VMware. So I'll demonstrate that after this. I don't have them running as a cluster yet, and I'll explain why when we get there, but it is up and running, and I'm pretty surprised. But anyway, we'll go through this first. Chapter 5, CPU optimization. This is actually not going to take a long time. So it's 3 lessons, and they're all pretty short. A review of CPU virtualization from the prior module. The CPU scheduler is crucial in providing enough resources from the CPU to your virtual machines. Without it, we can't run our VMs. It's aware of non-uniform memory access as long as your CPU can handle that. The processor and cache topology. If you ever see the virtual machine worlds, it's basically a thread. It's a process. So just like if you ran Task Manager and you see how many tasks are running, each one of those tasks would be considered a world in the realm of VMware. Why do they make things confusing? I don't know. It's kind of like iSCSI, where the target is the server and it's not the client, but whatever. Yeah, every item. So like your graphics, your mouse, keyboard, and screen, your CPU, all of these are their own little processes, and VMware just calls them worlds. Your CPU scheduler, which you don't necessarily work with, and it really just works behind the scenes. It coordinates and allocates the CPU resources, pinging every CPU to see which is getting overworked so we can move work to another virtual CPU. When working with physical CPUs, it can introduce queuing so that everything gets worked on time. Anything that has priority by resource allocation or reservations or whatever will get handled first, and then everything else afterwards. So when you set up those reservations, this takes over in ensuring that these devices get service first. It has co-scheduling with SMP to handle things more efficiently. The co-scheduling is a technique that it uses. Again, this is all really nitty-gritty stuff that happens behind the scene. The skew is a difference in execution rates between your vCPU and SMP virtual machine. The skew increases when it's not making progress, but one of the sibling CPUs is. The relaxed co-scheduling technique is a subset of a virtual CPU simultaneous after that skew is detected. An idle CPU doesn't have any overhead because it's doing nothing. Your performance, things that affect your CPU, of course, idling virtual machines. The CPU affinity, the constraints the schedule has, that can cause an imbalanced load. SMP virtual machines, anything that's co-scheduled can impact the performance, and insufficient CPU resources for demand. If there's a lot of demand for processing, but there's not a lot of processors, that can also cause problems. Ready time, if you see this, will be the amount of time a virtual CPU waits for the physical CPU to be available. If you start seeing ready time going up, then that means the virtual has to wait for the physical to be ready. So that means the physical is working a lot. A world or a thread, as we normally know it, goes through various states just like a thread does when it's running, when it's suspended, when it's stopped. Here you see how VMware treats the threads. And it is definitely more complicated than your usual operating system. And that's, well, because this thing is doing more than just being an operating system. It's not just running Among Us and your browser and Discord and all that. It's running virtual machines, each of which having its own set of sub processes all at the same time. So it's definitely going to be more complicated. Here's a quick question, and if you're watching the recording, you can hit pause and try to answer. What tasks does the CPU scheduler perform? It was just mentioned in the slides earlier. And the answer is 3 of the 4. Lesson number 2. So this whole section depends on if your CPU has NUMA, the non-uniform aware. If it doesn't have it, this whole thing just throw out the window. I actually don't know if the Raspberry Pis have this. I'm going to say no. I'm going to say that that's more of an Intel AMD type of thing, but it could be wrong. Anyway, you can get memory access optimization for processors that support NUMA. Each CPU in a NUMA node will have a local memory directly connected to it. So processes can access this local memory faster than on a remote CPU of the same server. Helps with balancing the processor load. So the way this works, when a VM is powered on, it gets assigned a NUMA scheduler and a home node where it will work, what memory, which cores, what socket will it work. This can dynamically change as the system load moves. The OS ESXi will present the virtual CPUs and a virtual socket to each virtual machine to work in. Those are mapped to a P CPU and then mapped to the NUMA node. That's how they're all interconnected. These groups will be considered the NUMA client, and it uses that client to place the VMs on nodes to do things like load balancing. If a vCPU, if a VM has more cores than on a node, then it's split. So if you have a 10 vCPU virtual machine and you have 2 8-socket cores, well, each NUMA client will have its own home node and the cores will be counted. Hyperthreading will not be. It's strictly on the cores. So you see we have a 10 vCPU system. We have 5 of them set to one client, to one node, and the other 5 to another. When a wide VM is created, like the one shown before, the topology will be presented, and it'll do its best to load balance and take, for example, if it was a 12 vCPU, it'll take 6 of those and put them in one node and 6 on the other. It tries to do its best to stay balanced. Now all of this that was talked about really comes down to when you change this setting. The number of virtual CPUs and cores per socket affect the ability of the guest OS to optimize their cache usage. You configure it. You make this change when you change that CPU setting. Ensure that the number of virtual cores per socket does not exceed the number of physical cores per socket on your ESXi host. That is the key to this. That is the key to ensuring we're optimizing our usage of the cores. Is that phrase right there. So again, if you have a 10 vCPU and 1 core per socket, then it should run on a dual socket 8 cores per socket system. Now, if we change the core per socket to 5, we get 2 sockets. And this will better align with our system. It'll be evenly spread. So here's a question. For optimal guest operating system performance, what should the number of cores per socket be for a 12 vCPU running on a dual socket 10 cores per socket system? And the answer, 6. Because it aligns with the physical characteristics of the system. Does that make sense? You want to evenly distribute your load. Memory considerations. When the topology is calculated, the compute dimensions are considered. So you always want to ensure that you have enough memory. For example, if an ESXi host has 2 sockets, 10 cores per socket, and 128 gigabytes of RAM per NUMA node, you're going to need a total of 256 gigabytes of RAM on the host. Continuing with that example, you can create a virtual machine with 96 gigabytes of RAM, 1 socket, and 8 cores per socket. For this VM, ESXi will create 1 single NUMA node, and it'll fit into that single physical NUMA node. If you create one with 192 gigabytes, 1 socket, 8 core, it'll still create 1 VNUMA. The VM will span 2 physical nodes, though, in order to get that extra amount of RAM loaded. So part of memory will be remote because we have 128 that are dedicated to these cores, but then this extra has to go from another node, and that node is now remote. It's no longer our home node. If the VM is memory intensive, the optimal configuration for the same VM that we were just talking about is 2 sockets and 4 cores per socket. That way it distributes the NUMA nodes into 2, splits the RAM up, and uses each of the nodes. This would be a more efficient VM. So here are some guidelines for you when you're using VNUMA. And then our last lesson, monitoring CPU activity. So you can use ESX top, which is like HTOP. You could run this locally on the shell or from the command line interface. It works just like top. So you have some of the common things like the CPU screen, memory, disk, and so on. You can customize the headers, customize what you see. Each resource will have its multiple columns, and you can choose which ones to display. Some of the most interesting performances that you could load up are these. But it really depends on what you're doing. In ESX Top, a group is a resource pool, a running VM, or a non-VM world. So for worlds that belong to a VM, you have the statistics of the running VM shown by the group ID. So you can definitely use ESX Top, kind of see the core's usage, each of the core being used, the number of VMs per virtual CPUs, the average load for the past minute, 5 minutes, and 15 minutes. You're going to enter V to just see the output of the VMs themselves. You can do E to see all the worlds associated with a single virtual machine. So you would pick a specific group, and then from there you'd see exactly what's running from that VM. And you can get even the virtual CPU information off of a specific VM. Things that you always want to watch out for are the high usage values and the ready time. There's the ready time. There's your usage. So the used and ready columns will show you when things are getting overcommitted. If you are trying to figure out CPU issues, here is a general way, a general flow chart to answer questions to figuring out what's the problem. Of course, if your CPUs are getting saturated, you might want to reduce the number of VMs running on that host. Maybe you need to add it in a DRS cluster. You might probably need to be more efficient in your usage of CPU resources or direct resources from to other critical VMs. Quick question, which of the following metrics can give you an indication of memory contention? Memory, not CPU. And the answer is that one. World spend waiting. That's what that means. To swap. And you can monitor the virtual CPU usage. If it's between 75 and 90, then you have a CPU saturation, which is not good. You can also monitor virtual machine usage for all virtual CPUs in an SMP virtual machine. If the average is under 75%, then the guest CPU usage is low. And here are some other causes and solutions. And you'll have a lab to do. Any questions? Like I said, this wasn't too long. It's pretty straightforward. Okay. So let me stop this recording.